So in the next lecture, we will look at position, velocity and acceleration in multi-body systems. Before we go to mechanical systems with several rigid bodies, let us recapitulate how we can represent the translation and orientation of a rigid body using homogeneous transformation matrices. So this picture shows a rigid body with respect to a coordinate system A, so XA, YA, ZA and the origin OA. There is a coordinate system B which is attached to this moving rigid body with XB, YB, ZB and the origin OB. Any point on this moving rigid body in its own coordinate system is given by BP, and in the reference coordinate system is given by AP. The origin of the B coordinate system is given by this vector AOB. So to represent combined translation and orientation of this rigid body B with respect to the A coordinate system, we propose to use a 4x1 homogeneous coordinates, in which basically we had this position vector, we added a 1. So our normal position vector is 3x1. We added another equation which was 1 equals 1, and then we combined the position, translation as well as the orientation of this rigid body using this 4x4 homogeneous transformation matrix, and we would obtain an expression which is A capital P, which is ABT into B capital P, where A capital P and B capital P are 4x1 homogeneous coordinates. So these are nothing but the position vector which is 3x1, and we concatenate a 1 with that 3x1 position vector. The 4x4 homogeneous transformation matrix ABT is formed from the rotation matrix which is ABR and the position vector locating the origin of the B coordinate system. So this part is a 3x3 rotation matrix, and this is a 3x1 column vector, and the last row is 00001. See, the upper 3x3 matrix, if it is identity, then it is a pure translation of this rigid body. If the top 3x1 vector is 0, then it is a pure rotation. So this homogeneous 4x4 homogeneous transformation matrix represents position of the origin as well as the rotation of this rigid body with respect to the A coordinate system. So let us continue. Now we have this rigid body undergoing successive rotations and translations. Okay, so we have one rigid body, or another way of saying is there are several rigid bodies connected one after another. So we have a rigid body B which is XB, YB, ZB, OB, and then this rigid body moves to C which is XC, YC, ZC and so on. Or we have a sequence of rigid bodies which is reference A, one fixed reference, then a rigid body B, then a rigid body C and so on, all the way to our rigid body N, which has the origin as ON and XN, YN, ZN. And if we have a point on this rigid body, then again we can find the position vector of this point with respect to the nth coordinate system, and then we can find the vector with respect to the fixed reference A coordinate system. In order to do that, we need the transformation matrix from A all the way till N. So N with respect to A, the 4x4 homogeneous transformation matrix is nothing but a product of all these matrices. So we go from A to B, B to C, all the way till n-1 to n. Each of these are 4x4 homogeneous transformation matrices containing both rotation and translation. So the position vector of this point P, the 4x1 homogeneous coordinates, with respect to the A coordinate system. A capital P is nothing but A, B, T, B, C, T all the way till n minus 1 T into NP, where n capital P is nothing but this position vector n small p with a 1 added at the end. The fourth element is 1. So hence we can find the position and orientation of any rigid body with respect to any other rigid body. So for example, if I want to find between I, j with respect to I, so all I need to do is multiply suitable homogeneous transformation matrices. So if I want to find what is C with n, so I will go from C to D, D to E and so on, all the way from n minus 1 to n. So we multiply all those transformation matrices and we get from C to n. Now let us look at the position in multi-body systems, and we will start with serial chains. Okay, so remember in serial chains we have a link, a joint, a link and a joint. One end is fixed and one end is free. So this picture shows two rigid bodies connected by a rotary joint. We will look at other kinds of joints also. So what is the goal? We know the position vector of the ith link, and we want to know what is the position vector of the I plus 1th link. So I know OI1, O0 OI, and then I want to find out 0 OI plus 1, and we assume that these two rigid bodies are connected by means of a rotary joint. Recall, a rotary joint allows this I plus 1 rigid body to rotate with respect to the rigid body I about an axis along K by an angle theta. So the second rigid body is a function of one joint variable theta. Okay, the rotary joint allows 1 degree of freedom. So the position and orientation of this rigid body with respect to this previous rigid body can contain only one independent variable, which is theta. So I minus 1 I, this transformation matrix, is a function of theta alone. Okay, so the rigid body I with respect to I minus 1 will be a function of this rotary joint theta if they are connected by a rotary joint, as shown in this figure. If it was a translatory joint, if this joint was a prismatic joint, then I minus 1 IT would be a function of the translation along this prismatic joint, which we denote by D. So in a serial chain, the n rigid bodies are connected by R and P joints. That is what we will look at in this course most of the time. So hence, the last link or the last rigid body n with respect to the fixed reference frame or 0, the transformation matrix is nothing but a product of 0, 1, 1, 2, n minus 1 t, and this right hand side will be a function of n joint variables. So if there are n rotary joints, then each one of these transformation matrix is a function of theta. So there are n thetas. If there are some thetas and some d's, then these n joint variables are broken up into thetas and d's. Theta is the rotation at the rotary joint, d is the translation at the prismatic joint. So in a serial chain containing multi-degree of freedom joints, so for example, if there was a spherical joint, we would have to replace that spherical joint either with 3 rotary joints or some other combination. So if it was a cylindric joint, which is normally not used, then we would have a R and a P joint. In a parallel system or a parallel mechanism or with loops, okay, there are multiple loops. Okay, as I had mentioned earlier in the structure, so we had a serial chain, we had a parallel chain, and we had tree structure and so on. So in a parallel system, we have multiple loops. So this is an example of a parallel robot. this is the 3 degree of freedom 3 RPS robot. So the RPS comes from each chain has a rotary joint, a prismatic joint, and a spherical joint. So that there are 3 such chains. And what you can see is I can start from some, let's say, one fixed rotary joint. I can go to prismatic joint. I can go to a spherical joint. I can come to this spherical joint and come back to the fixed base. So this is one loop. So we can have another loop which is this R, P, S, this S which is S2, and then come back here. So there are 3 possible loops. So in a parallel system there are multiple possible loops. And there is no clear and well-defined free end of as in a serial chain. So in a serial chain, one end is fixed and one end is free. So in this case, which is the free end? Okay, so once somebody can say that this is my free end, which is reasonably good choice, but somebody can say that this link is my output and this is my free end. So we need to choose what is the free end and which is the output rigid body in parallel systems and parallel mechanisms and parallel robots. So the position vector of a point chosen on the output requires the use of a combination of this 4x4 homogeneous transformation matrix, and we need to use loop closure and constraint equations determined by the geometry in the mechanism. So for example, in this mechanism, if I want to find this point, which is the, let's say, one point on the output link, I can use the 4x4 homogeneous transformation matrix corresponding to this rotary joint, this prismatic joint, and then spherical joint, which will have to be considered as 3 rotary joints, and then come to this point. Okay, so this is one possible way to come to this. But we could have also come in some other way. So we would need to use what are called as loop closure constraint equations to really obtain what is the output link, and the output link as a function of the actuated joint variables. So in this 3RPS parallel mechanism, we can show that it has 3 degrees of freedom. So there are only 3 possible actuated joints. So most of the time these prismatic joints, this one translation here, one translation here, and one translation here are the 3 actuated joints. We need to find expressions for these 3 rotary joints and even maybe for the 3 spherical joints. So we need to use what are called as loop closure equations to obtain the expressions for these rotary joints and what is happening at the spherical joints. And there are several ways to obtain these constraint equations, and in a parallel robot it is easier, but in a 3D system like this it is much harder. Okay, so for example, in this parallel robot, in this simple parallel mechanism, which is a 4-bar mechanism, there are 4 links. One possibility is this is the input and this is the output. So we have basically one single loop and it is in a plane. It is the simplest possible parallel system, and we can say that this is my output. Somebody else can say that this second link, link 2, which is sometimes called the coupler, is the output. So we need to choose what exactly is the output in any parallel mechanism, and this 4-bar illustrates the point very clearly. Okay, in many kinematics books or kinematics of machinery, this is the output, which is the output link, and this is called the crank. And sometimes when you want to guide a rigid body through some positions, then the coupler is chosen as the output link. So there are no general approaches as in a serial chain to choose which is the input and which is the output. Okay, and also which is the fixed and which is the free end, and how do we go from the fixed to the free end. Okay, there are no general approaches in case of parallel systems. So we need to make sure that we need to choose which is my output link, and then we do the analysis. So let us continue. In a parallel system, we can obtain the position of the output link. If we choose this as the output link, then we can find the centroid of this top moving platform as my position of interest, okay, of this output link of interest. So how do I find the centroid of this top moving platform? This can be obtained by once we know what are the position vectors locating these three spherical joints. Okay, so if I know what is the position vector of S1, S2 and S3, which are the three spherical joints, from a fixed reference coordinate system, which is X, Y and Z with origin 0. So I want to know this vector. So if I know this vector, if I know the second spherical joint S1, S2 and S3, then the centroid is nothing but 1/3 of the sum of these three vectors. So as you can see, I am denoting this vector as base S1, which is the base platform is a coordinate system which is called base with X base, Y base and Z base and origin. And this vector is from the origin of the base coordinate system to S1, S2 and S3. So if I can know these three vectors, then I can find the centroid. This is the formula for a centroid, knowing 3 points of a triangle. The orientation of the top platform can also be obtained once I know these three locations of these spherical joints, okay, or 3 points on this moving platform. So the first x-axis can be assumed to be from S1 to the centroid. So this vector base P minus base S1. So base P is this vector, base S1 is this vector. So the difference of these two vectors will be along this arrow, okay, along this vector. And then we can find it as a unit vector, which is nothing but this vector divided by the magnitude of this vector. We can also find what is the normal to this plane. So we can find base to P, okay, so P base minus PS1, which is this vector. We can also find base to P minus base S3, which is another vector which is along this direction, and the cross product of these two vectors will be normal to this plane. Again, we can divide by the magnitude to make it as a unit vector. So this vector is the z-axis, this is the x-axis, and y-axis is the cross product of z and x. So remember, the rotation matrix is nothing but the x, y and z axis along the columns. So the first column is the x-axis, third column is the z-axis, and the second column is the y-axis, which is nothing but z cross x. So we can find the orientation of the top platform with respect to the base, or the moving platform with respect to the base. Again, if I know these three locations of these three spherical joints. The angular velocity of the top platform can be obtained from r dot r transpose. Again, this base and top tells us what is the angular velocity of which platform or which rigid body we are interested in. So here we are interested in the angular velocity of the top platform with respect to the base, or the moving platform with respect to the base platform. And once I know what is the rotation matrix, we can do r dot r transpose. This will be a skew symmetric matrix, and I can extract the three components of the angular velocity vector. So let us now go back to serial chains. So I want to find formulas for finding the angular velocity and the linear velocity of one rigid body connected to a previous rigid body by means of a rotary joint. Okay, so first we will look at rotary joints. So then for two rigid bodies connected by a rotary joint, the rotation matrix of the ith with respect to the fixed reference 0 is nothing but 0 minus 1 into what is happening at the rotary joint. So remember, at the rotary joint we are only allowing a rotation of theta I with along k axis. So we can find the rotation matrix and then we can pre-multiply this rotation matrix with the rotation matrix of the ith I minus 1th rigid body. So 0 I minus 1 into I minus 1 I will give me the rotation matrix of the ith rigid body with respect to the 0th rigid body. So if you take the time derivative of this equation, I want to find out the angular velocity. What happens to the angular velocity of the second rigid body with respect to the previous rigid body? So we need to take the time derivative of this. If you take the time derivative and do some simplification, you can show that this r dot r transpose, okay, of the left hand side is nothing but this d by dt of r, so 0 ir into I minus 1 ir into I minus 1 ir into 0 I minus 1 r transpose. So we are trying to find out what is the angular velocity, the space fixed angular velocity, if you recall, which is r dot r transpose. And this follows from the derivative of left hand side, and this follows from the derivative of the right hand side. So since k is fixed in I minus 1 and I, so k is the common axis about which the second rigid body is rotating with respect to the first rigid body. So we can rewrite this equation as the space fixed angular velocity of rigid body I is nothing but the space fixed angular velocity of rigid body I minus 1 plus theta dot along the k axis. It is very sort of obvious. So I have an angular velocity of the first rigid body. The second rigid body is connected with the first rigid body by means of a rotary joint. The rotary joint is allowing a rotation of the second rigid body with respect to the first. So the angular velocity of the second will be nothing but the angular velocity of the first plus what is happening at the rotary joint. So this is exactly this equation written in a formal mathematical form, which we can use later on for analysis. So if you pre-multiply this equation with I0R, so what is I0R? It is nothing but the transpose of this rotation matrix. So I0R is 0 with respect to I. Okay, till now we were doing I with respect to 0. So this is 0 with respect to R. So that is nothing but the inverse of the rotation matrix, which is same as the transpose. So if you pre-multiply both sides of the equation, what you can see is you will get I0 R into 0 omega is. So again 0 and 0 sort of cancels out in your mind, and we are left with I omega I on the left hand side. On the right hand side we will have I omega I minus 1, and then we have I ki theta I dot. So what is I ki? So what is the k axis in its own coordinate system? Depends on what is chosen as the k axis. Most of the time the rotary joint is assumed to be along the z axis. Okay, so I ki is nothing but the z axis in its own coordinate system, hence that is 0, 0, 1. So this term will become theta dot I 0, 0, 1, okay, column vector. Whereas this term I omega I minus 1 can be rewritten as I minus 1 R I minus 1 I omega I minus 1. Okay, so again simple matrix multiplication. So if you pre-multiply this I minus 1 omega I minus 1 with this rotation matrix I minus 1. So basically I minus 1 with respect to the ith coordinate system opposite. Remember, we are going from I minus 1 to I, but this is telling you what is the rotation matrix of I minus 1 with respect to the next coordinate system. So we will get this. Okay, so one important thing in this equation is that this I omega I is not necessarily 0. What is I omega I? It is nothing but this angular velocity of the rigid body I with respect to the 0 coordinate system, but expressed in the ith coordinate system. Okay, so we know what is 0 omega I, that is nothing but this r dot r transpose, and we want to pre-multiply by I 0 r, and that is what we are denoting as I omega I. It is not necessarily 0. Okay, we will take a look at this next few slides to give a more interesting interpretation of what is I omega I and why it can not be 0 all the time. Okay, so in this picture, as a summary, what do we have? We have this rigid body I, we have another rigid body I minus 1. So the angular velocity of this rigid body I with respect to I minus 1 is nothing but the angular velocity of this rigid body I minus 1 plus the rotation at this rotary joint. Okay, so these are two vectors. We just add them in the same coordinate system and we get the angular velocity of this rigid body I with respect to I minus 1 when it is connected by a rotary joint. Okay, now let's look at what is exactly this I omega I in a little bit more detail. We know from a previous week that the space fixed angular velocity vector, which is 0 omega I s with a superscript s, is related to the body fixed angular velocity vector 0 omega I with a superscript b as in this form. So this is r dot r transpose, this is r transpose r dot. Okay, if you go back and see your previous lectures, this is r transpose r dot. So we can pre-multiply by a rotation matrix and we can get the space fixed angular velocity vector. Okay. So now let us pre-multiply both sides by I0R. So again, basically I0R is nothing but 0 with respect to I. Okay, the previous fixed coordinate system with respect to the moving coordinate system. So it is in some sense inverse of I0IR. Okay, so let us pre-multiply both sides of the equation by this matrix. So I have I0R into 0 omega I. This will give me I omega I. And what is happening to the right hand side? I have I0R, which is this, and multiplying 0IR, which is as before. So now the product of these two matrices is nothing but identity, because this is okay 0 coordinate system with respect to I, and this is I coordinate system with respect to 0. Again, in our mind, if you think of this as two matrices, we can cancel the zeros and we have I R I. So there is no rotation. So this is an identity matrix, and hence we are left with only this term, which is 0 omega I b. So what this simple algebra is showing you, that this quantity, which is I omega I, is nothing but this body fixed angular velocity vector. Okay, and hence I omega I is not necessarily 0, because the body fixed angular velocity vector need not be 0 all the time. So finally, what we are left with is that I omega I is same as I omega I minus 1 plus I ki theta I dot. Okay, so in serial chain, as I have mentioned last slide, that the rotate R joint axis is typically along the Z axis, and hence I omega I can be written as I minus 1 R, I minus 1 omega I minus 1 plus theta dot multiplied by 0, 0, 1. So what is the nice feature of this formula? We can start with, let's say, I equals 1. So when you put I equals 1 in this formula, we have, what is this? 0 omega 0. Okay, so typically what is 0? That is the fixed or the reference coordinate system, which is not typically rotating unless it is on some complicated system where the base itself is moving. Okay, so then this we can find the right hand side. We know what is happening to at the first joint. which is I equals 1. Remember, theta 1 is the first joint. So this is about the z-axis. So this formula will tell you what is the angular velocity of the first link with respect to the previous link. Then we can put I equals 2. Then the right hand side is 1 omega 1, which we have obtained from the previous step. And then this will give me 2 omega 2. Okay, so I can basically go from the fixed base all the way to the free end every time, and we add this what is happening at the rotary joint, and I can get the angular velocity of each of these links in a serial chain. This is a very useful formula. These are called angular velocity propagation formulas in rigid bodies connected by R joints. We can also find what is happening to the linear velocities of each rigid body with respect to the previous rigid body. Okay, and this comes from this basic expression for the position vector of a point on the second rigid body with respect to the first rigid body. So we can see that this origin OI or 0 OI is nothing but the 0 OI minus 1 into I minus 1 to I. Okay, and then we have to pre-multiply by this rotation matrix so that it is all consistent. Okay, so here is an example. So what we have is this 0 OI, which is the vector which is locating the origin of the ith coordinate system. It is nothing but the vector which is from origin of the fixed or the reference coordinate system to the origin of the I minus 1 coordinate system or the I minus 1 rigid body, and then the vector from the I minus 1 origin to the ith origin. Okay, so this vector is nothing but this plus this, but we cannot simply add two vectors in two different coordinate systems. See, this is I minus 1 OI, whereas this is 0 OI and this is 0 OI minus 1. So we have to pre-multiply by a rotation matrix. So from this expression, I can take the derivatives of both sides and I get the velocity of the origin of the ith coordinate system or the ith rigid body is nothing but the velocity, linear velocity of the I minus 1th origin or the rigid body I minus 1 plus some omega cross r. Okay, we can show that this will lead to the derivative of the second term will lead to something like omega cross r. And again, we can say that this we need to do it properly so that the omega is in the 0th coordinate system and then this r is also in the 0th coordinate system. Okay, in the fixed reference or 0 coordinate system. So this is a well-known formula. We are now, we are putting all kinds of superscripts and subscripts just to make it very formal, that if you have whole bunch of rigid bodies, then we can relate the linear velocity of the ith rigid body in terms of the I minus 1th rigid body. Both of them are connected by a rotary joint as nothing but the linear velocity of the origin of the I minus 1 rigid body into some omega times r. Okay. And again, we can pre-multiply by a rotation matrix I 0 r. So basically I with respect to 0, and then we will get a term which is I vi, and then this term will be I minus 1 I to I minus 1 r, I minus 1 vi, I minus 1 omega I minus 1 into I minus 1 0 or origin I. Okay, so just pre-multiply the previous equation with I to 0 rotation matrix. Okay, and then rearrange and we will get this. So this is also a propagation formula for the linear velocity vector. So if I know what is the linear velocity of the origin of the I minus 1 rigid body or the coordinate system origin of the I minus 1 coordinate system, and then I know that the second rigid body is connected to the first rigid body by means of a rotary joint, then we can do this. So just add this velocity with omega cross r. Okay, and again this I vi and I minus 1 vi are not necessarily 0. Okay, so what is I vi? It is nothing but the linear velocity of the origin of the ith rigid body with respect to 0, but pre-multiplied by a rotation matrix. And what does this pre-multiply by a rotation matrix means? We are expressing it in another coordinate system. And the same story is what is happening to I minus 1 vi minus 1. It is nothing but the linear velocity of the I minus 1 rigid body, or the origin of the I minus 1 rigid body, okay, and then pre-multiply by a rotation matrix. So these quantities are not necessarily 0. Remember, we had discussed this much earlier, that the derivative of a position vector will give the linear velocity, but I can express this linear velocity in some other coordinate system. So this is exactly what we are doing here. We are finding the derivative in the 0th coordinate system, but we are expressing it in the ith coordinate system. Or for I minus 1 rigid body, we are finding the derivative in the 0th coordinate system, but we are expressing it in the I minus 1th coordinate system. So this is just a way to show that we can go from fixed base, which is normally 0 velocity, then we can keep on adding these omega cross r terms and this I minus 1 vi terms to obtain the linear velocity of all rigid bodies in this serial chain. And in this case, we are assuming all the serial rigid bodies, all the rigid bodies in this serial chain are connected by R joints. So this formula is very well known and it is used in many serial chains. It is nothing but the linear velocity vector propagation in rigid bodies in a serial chain with R joints. Now let us look at if the rigid bodies are connected by prismatic joints. Prismatic joints are the one which allows relative translation between the two connected rigid bodies. Okay, only relative translation is allowed. So if only relative translation is allowed, then the angular velocities of these two rigid bodies will be same. Okay, there is no rotation happening at the joint. Okay, so the second rigid body and the first rigid body will have the same angular velocity. So here is a figure. So I have a rigid body I and I have a rigid body I minus 1. They are connected by this prismatic joint, which allows translation along this joint axis, and the variable which represents translation is di. And again we have all these different axes and the origin of the I minus 1th rigid body and the origin of the ith rigid body. Okay, so if the relative translation is along the z-axis, meaning we choose that the k-axis is the z-axis, which is very commonly used in robotics or in many multi-body systems, that the joint axis is chosen as the z-axis. So what is the relative translation? It is di dot along 0, 0, 1. Okay, so di is the translation, so the derivative is denoted by di dot. And what is the velocity propagation for the prismatic joint? As I said, the angular velocities are same. So the angular velocity of this I minus 1 is the same as the angular velocity of I. And again, we rewrite in this form that I omega I is nothing but I minus 1 omega I minus 1. But we have to write both these left and right hand side in the same coordinate system. So we pre-multiply by a rotation matrix I minus 1 R. So remember, what is I omega I? It is nothing but the body fixed angular velocity vector of the rigid body I in the 0th coordinate system. Remember, I had proven this earlier. Likewise, the linear velocity of the ith rigid body can be written in terms of the linear velocity of the I minus 1 rigid body. So what will it be? It will be nothing but this velocity vector will be equal to this velocity of the I minus 1 plus some omega cross r, but now we have a translation along the z-axis because the second rigid body can translate with respect to the first rigid body along this direction, along this k, which is chosen as z, which is 0, 0, 1 for this example. So we have I minus 1, Vi minus 1, some omega cross r, and then this di dot, and we would like to write in this recursive or this propagation form, which is I Vi some matrix multiplication into I minus 1 Vi minus 1 plus omega cross r plus di dot. Okay, and again this I minus 1 r, I minus 1 omega I is nothing but I omega I, which is the body fixed angular velocity vector of rigid body I. Okay, so it is 0 omega I with a superscript b. And the same story is with IVI. They are not both zeros. So IVI is nothing but the linear velocity of rigid body, but written in a different coordinate system. So let us continue. Let's look at velocity and acceleration in multibody systems, and we want to look at parallel systems. So to repeat, I have said this many times, that there is no clear free or last rigid body in a parallel system. Okay, so most of the time the moving platform is chosen as the free end. The centroid of the top platform or any other point of interest can be obtained with respect to the fixed or the base coordinate system by a vector. The linear velocity of this centroid is nothing but the derivative of this with respect to time. The angular velocity of this moving coordinate system is nothing but r dot r transpose. Okay, so this is the space fixed angular velocity vector. The linear acceleration of a point on this moving platform, in particular if it is the centroid, then it is nothing but the second derivative of this position vector. So we can find the second derivative, and then that will be the acceleration of this point. The angular acceleration can be obtained from the derivative of the angular velocity vector. Again, I have said it earlier, going from rotation matrix to angular velocity requires you to compute this r dot r transpose, then find the skew symmetric matrix, and then extract from that skew symmetric matrix the x, y, and z components. Whereas if you want to go from angular velocity to angular acceleration, all you need to do is just take the derivative, because this is now a vector. We don't have to worry about this r dot r transpose and so on. So let us look at propagation of velocity in summary. So for an r joint, the angular velocity of the ith link in terms of the I minus 1th link is nothing but the angular velocity plus theta I dot 0, 0, 1, assuming again that the rotation axis is the z axis. And again, all this pre-multiplication by a rotation matrix is to write it in a suitable convenient form. Similarly, the linear velocity of this ith rigid body is nothing but the linear velocity of the previous rigid body plus omega cross r. Again, all these matrices and other things have to make it consistent and write it in a suitable form, in a desired form. If you have a prismatic joint, then the linear velocity of this prismatic joint will be the linear velocity of the previous rigid body. So linear velocity of the ith rigid body will be nothing but the linear velocity of the I minus 1th rigid body plus some omega cross r, but we now have to add the translation at this prismatic joint. Okay, and how about the angular velocity? The angular velocity of these two rigid bodies are same, because the prismatic joint does not allow any relative rotation. It only allows relative translation. So this is what is written in these two equations. So I omega I is nothing but I minus 1 omega I pre-multiplied by a rotation matrix to make it consistent. And again, I omega I is nothing but the body fixed angular velocity vector of rigid body I written in the ith coordinate system. Okay. And similarly, the linear velocity of this rigid body I described in the ith coordinate system is nothing but the linear velocity of the previous rigid body plus omega cross r plus what is happening at this prismatic joint, which is di dot 001. The propagation of acceleration is a little bit more interesting, and we start again with the linear and angular acceleration of rigid body I with respect to the zero coordinate system. So as I said earlier, the angular velocity of rigid body I with respect to the reference coordinate system or the zero coordinate system is nothing but the angular velocity of the I minus 1 with respect to the zero coordinate system. S stands for space fixed plus the rotations at the joint. This is when it is connected by a rotary joint. The linear velocity at the origin of the ith coordinate system is nothing but the linear velocity of the origin of the I minus 1 at coordinate system into some omega cross r. Okay, so this omega cross r has to be done properly because this vector I minus 1 OI, we cannot take the cross product with a vector which is 0 omega I minus 1. So we pre-multiply so that these two together is a vector in the 0th coordinate system. So the derivative of these two will give the acceleration because these are vectors. Pre-multiplying the derivative rotation matrix and writing in the form for propagation, we can show that the derivative of vi dot with respect, again written in the ith coordinate system, is again something which is very similar in concept. It is nothing but the acceleration of the I minus 1th coordinate system. Okay, again with some superscript I minus 1. Then it is some alpha times r. So omega dot I minus 1 is nothing but the derivative of the angular velocity vector, which is nothing but the angular acceleration, plus some omega cross r. Okay, so most of you would have seen this expression that the acceleration when you have two rigid bodies connected by a rotary joint is the acceleration of the previous rigid body, then omega cross alpha cross r, and then omega cross r. So this is like the centripetal acceleration. The angular acceleration, when we take the derivative of this, is nothing but the angular acceleration of the previous rigid body and then what is happening at the joint, which is theta double dot I along z axis. But more interestingly, we also have another term. This will appear if you do properly. What it tells you is that we have a term which is omega I minus 1 into theta dot along the z axis. Okay, so this is normally not seen when you are considering a single rigid body. But if you have a whole bunch of rigid bodies which are connected by rotary joint, what is happening at theta dot I along the z axis, this is a vector, and you can take the cross product of this I minus 1 omega I minus 1 into this vector. This will also contribute to the acceleration of the ith rigid body. Okay, and again we need to pre-multiply by some rotation matrix to write it in this correct form, in a propagation form which is suitable for propagation. So this term is normally not seen if you are considering only a single rigid body, but this will appear if you do take these derivatives properly. So as I said, the rotation axis is taken as the z-axis most of the time. Note that there is no Coriolis and relative acceleration term when you have the two rigid bodies connected by a rotary joint. Okay, so Coriolis acceleration happens when there is a relative velocity of a point on the ith rigid body. Okay, so a point on the ith rigid body is moving in its own coordinate system with some velocity or with some acceleration. So then we get these two terms. Remember, in the acceleration expression there were 5 terms. Here there are only 3 terms. Which are the 2 terms which are missing? The Coriolis term is missing and the relative acceleration term is missing because they are not there when you have two rigid bodies connected by a rotary joint. Okay, and I have, as I said a little while back, this is a interesting term. Okay, this term, which is I minus 1 omega I minus 1 cross theta dot I along the z-axis, arises from the derivative of this k-axis. Okay, so if you have several rigid bodies, the k-axis of one is not the same everywhere. The k-axis is also rotating, and this is what gives this term. So the propagation of acceleration when two rigid bodies are connected in a serial chain with a prismatic joint is very straightforward. We start with the propagation of angular velocity and linear velocity. So these expressions have been given earlier. The angular velocity of the ith rigid body is same as the angular velocity of the I minus 1th rigid body. The linear velocity of the ith rigid body, which means the linear velocity of the origin of the coordinate system attached to this ith rigid body, is nothing but the linear velocity of the origin of the previous rigid body plus some omega cross r, and this is the translation at the prismatic joint. If you take the derivative of both these equations, so let's start with the simple one. If I take the derivative of the angular velocity equation, we can see that the angular acceleration is nothing but the same as the previous one. Okay, so I omega I dot is nothing but I minus 1 omega I minus 1 dot, again pre-multiplied by a rotation matrix so that it is in a propagation form suitable for propagation. But let us now take a look at this derivative of the linear velocity. So we have 3 terms here, one which is the velocity of the origin, then some omega cross r, and then this is di dot. Okay, what is happening at the prismatic joint. Now in the second rigid body there is some relative motion in its own coordinate system because of this di. So hence we will have Coriolis term, and then we will also have the relative acceleration term, which is what shows up here. So we have some 2 omega cross v relative plus a relative. Okay, both of these, a relative is along the z-axis and 2 omega cross will be 2 I omega I cross di dot along the z-axis. Plus, of course, we have the other terms, which is the centripetal acceleration term, then alpha times r, and the acceleration of the origin. So when you have two rigid bodies connected by a prismatic joint, we have all the 5 terms which are seen in the acceleration, okay, of a rigid body in 3D space. So in this case, it should be noted that the Coriolis and relative acceleration term arises due to the translation at the prismatic joint. So you can think of this expression that the prismatic joint allows the relative motion of the second rigid body with respect to the first rigid body. So it's similar to the ant example which we did for a plane. So we have a rotating coordinate system or some moving coordinate system, and then this ant is moving inside in that coordinate system itself. So in this case, the ith rigid body is moving with respect to the I minus 1th rigid body due to the joint. And again, in this example, or in many other examples, we will take the k-axis as the z-axis. If the k-axis is some other axis, these expressions will be much more complicated. So let us look at the example of a planar 3 degree of freedom robot, because this is very simple and we can work it out on these slides and then you can work it out yourself. So what do we have here? We have 3 links, link 1, link 2, and this is the last link. So we have a fixed coordinate system which is x0, y0 with the origin here. This is labeled as 0 coordinate system. Then we have this link 1 which is rotating with respect to the fixed x-axis by theta 1, and the x and the y-axis are as shown here. Then we have the second link which is rotating with respect to the link 1 by another theta 2, and this is the x and the y-axis and the origin is here. And then we have the third link which is rotating with respect to the second link by theta 3, and this is the x and the y-axis for the third link. Okay, so this is x3, y3, this is x2, y2, and this is the origin, and this is x1, y1, and this is the origin. Okay, so this is an example in a plane. So all the z-axis at every coordinate system is coming out of the page and they are parallel to each other. So all links are connected by rotary joints. All joint axes are parallel and coming out of the page. These are the z-axis. So if 0 is fixed, then the angular velocity of the 0 with respect to 0 is 0. So these are obvious, right? So the basis or the fixed reference coordinate system is not rotating and not translating. So the angular velocity and the linear velocity, the angular acceleration and the linear acceleration, they should be all 0. Okay. Now we look at this I equals 1, which is nothing but this link. Okay, so for this link we have 1 omega 1 will be equal to something which is happening at the 0th link, so 0 omega 0 plus what is happening at the first rotary joint. The first rotary joint is 0 0 theta 1 dot. It's a column vector and this rotary joint is along the z-axis. So we can obtain what is 1 omega 1 by substituting in this propagation formula, and then you will get 1 omega 1 is nothing but 0 0 theta 1 dot. How about the first velocity? The origin of the first link and the 0th link is at the same place. So you can intuitively see that the origin of the first link O1 is not moving with respect to O0. So hence this is 0. You can also check it mathematically by going back to the propagation equation, and there you can see you will have one term which is linear velocity of I minus 1 and omega cross r. So the linear velocity of the 0th link is 0 and omega cross r is also 0 because r is 0. Likewise, the acceleration 1a1 is 0 and 1 alpha 1 is theta 1 double dot. For I equals 2, okay, we substitute back I equals 2 in the propagation equations and we will get 2 omega 2 as 0 0 theta 1 dot plus theta 2 dot. 2 alpha 2 will be 0 0 theta 1 double dot plus theta 2 double dot. The 2v2, what does 2v2 means? It is the velocity of the second link, which is the velocity of the origin of the second link, okay, expressed in the second coordinate system. So we first find out 0 v2 and then we pre-multiply by a rotation matrix 2 0 r. Okay, so 2 0 r, or it looks like this, and then if you expand it you will get L1 S2 theta 1 dot, L1 C2 theta 1 dot and 0. Okay, so you can sort of see that it looks okay. Why? Because theta 1 dot is what is happening here. The velocity of this will be related to L1 theta 1 dot, and this sine theta 1, sine theta 2 and cos theta 2 will appear if you do it consistently. The acceleration, on the other hand, will have the derivative of this with respect to the 0 coordinate system and then rewritten in the second coordinate system. You will have all these terms. So you will have minus L1 C2 theta 1 dot square plus L1 S2 theta 1 double dot, then L1 S2 theta 1 dot square plus L1 C2 theta 1 double dot 0. Okay, so recall this theta 1 dot square is similar to the centripetal acceleration. Theta 1 double dot is the tangential acceleration. There is no Coriolis term in this, and there is no relative acceleration because there is no relative motion happening. For I equals 3, which is what is happening at this origin of the third link, okay, that is the linear velocity of the origin of the third link. Again, we can go back and substitute in the formula. So 3v3 will be related to 2v2 plus omega cross r. Okay, we go back and substitute and you will get this expression, which is nothing but L1 S2 3 plus L2 S3 into theta 1 dot and something into theta 2 dot, and the y component will have the cosine of the angles. The angular velocity is nothing but theta 1 dot, theta 2 dot, theta 3 dot. So this is theta 1 dot, this is theta 2 dot, this is theta 3 dot. So this link will have the angular velocity of this plus this plus this, and it is sort of obvious because all the angular velocity vectors are coming out of the page. So if they are all connected by rotary joints, the last one will be the sum of all the previous ones. Likewise, the angular acceleration will be theta 1 double dot, theta 2 double dot, theta 3 double dot as its z component. The x and y components are both 0 for both angular velocity and angular acceleration. The acceleration of this third link, the origin of the third link, is much more complicated. So now you can see that you will get some theta 1 dot square, you will also get some theta 1 double dot, you will also get some theta 2 double dot, and you will also get some theta 1 dot plus theta 2 dot whole square. Okay, so these are the centripetal terms, this theta 1 dot square and theta 1 dot plus theta 2 dot square. These are, on the other hand, they are the tangential acceleration term. So there is a velocity which is happening theta 1 dot, and then there is theta 2 dot. Because of this theta 1 dot square and theta 2 dot square, there will be some centripetal acceleration term. Okay, the y component will have similar things, but now you have sine of theta 2 plus theta 3, cosine of theta 2 plus theta 3. Here it was sine of theta 2 plus theta 3, and so on. So there is some difference between sine and cos, and of course there are some changes in the plus and minus. Okay. Let us continue. Let us find the angular velocity and the linear velocity of the end effector, or the last or the free end of this robot, planar 3 degree of freedom robot. So this is the serial chain, first link, fixed link, one joint, another link, another joint, another link, another joint, and all the way to a free end. This free end is called in robotics the tool coordinate system. So basically this is where you would carry the tool which the robot will operate. So doesn't matter, in this mechanical systems we consider it to be the free end. So for the tool coordinate system, the angular velocity will be nothing but theta 1 dot plus theta 2 dot plus theta 3 dot. The angular acceleration will be the second derivative of theta 1, theta 2 and theta 3. The velocity of this tool coordinate system will contain theta 1 dot, theta 2 dot, and also theta 3 and all these angles, okay, in its own coordinate system. The acceleration is much more complicated. It is actually a long expression. Okay, but we can find it just by using the propagation equations which I have shown earlier. So in this case again we have some centripetal term, then we have some tangential acceleration term, and then we also have these terms which are theta 2 dot, theta 3 dot. So we have theta 1 double dot, then we have some theta 2 dot, theta 3 dot, which is also like a centripetal term, and then we have various other terms. Okay, so we can find these terms just by applying the expressions for propagation of acceleration. Finally, let us look at what is happening to the free end in terms of the fixed or the reference coordinate system, which is 0. Okay, so the angular velocity of the free end or the tool coordinate system is nothing but the angular velocity of the three joints. So theta 1 dot, theta 2 dot, theta 3 dot, all along the z-axis. The linear velocity of this is nothing but the expressions which are this. Okay, this one you can sort of see which makes sense. Why does it make sense? So let's look at the x coordinate of this point. So the x coordinate of this point will be L1 into cos theta 1. This is the projection. Then L2 into cos theta 1 plus theta 2, because the angle of this link with respect to the horizontal will be theta 1 plus theta 2. Then the angle for this link will be theta 1 plus theta 2 plus theta 3. So the x coordinate will be projection of this, which is L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and then L3 cos theta 1 plus theta 2 plus theta 3. So remember, they are all cosines. So now if I take the derivative in order to get the x component of the velocity, we will have minus L1 S1 into theta 1 dot, then minus L2 S12 into theta 1 dot plus theta 2 dot, and then minus L1 S123. S123 means sine of theta 1 plus theta 2 plus theta 3 into theta 1 dot plus theta 2 dot plus theta 3 dot. Likewise, the y component will be sine of theta 1 into L1, then sine of theta 1 plus theta 2 into L1 S1 plus L2 S12 and so on. And then when you take the derivative, you will have cosine L1 C1 into theta 1 dot. So if you think a little bit and look at your basic trigonometry from high school, this makes sense. So the velocity vector of this contains theta 1 dot, theta 2 dot, theta 3 dot, and also it contains all the sines and cosines. The linear and angular acceleration of this last free end with respect to the 0, the acceleration is very simple. It is nothing but theta 1 double dot plus theta 2 double dot plus theta 3 double dot. The acceleration on the other hand is much more complicated. Okay, so what should it contain? We can sort of intuitively guess that it will have some Coriolis term, not Coriolis term, some centripetal term. It will also have some tangential acceleration, and we can see that there will be some sine and some cosine of the angles. So, and that is what exactly you can see. So you will have theta 1 double dot, theta 2 double dot, theta 3 double dot into some L3, and similarly L2 into theta 1 double dot plus theta 2 double dot, and then L1 into theta 1 double dot. So these three terms are the tangential acceleration. This is like alpha times r. And then we have three other terms which are theta 1 dot plus theta 2 dot plus theta 3 dot whole square. This is the centripetal term. This is another centripetal term which is theta 1 dot plus theta 2 dot whole square. And then there is this theta 1 dot square. Okay. In the case of the y component, again you will have these similar terms, but now instead of cosine theta 1, 2 and 3, you will have sine theta 1, 2, 3. Okay, so wherever there is a sine here for the tangential acceleration, you will have a cosine. So it sort of makes sense, and you can show that this is indeed correct and true. Unlike the serial chain which we have discussed, if you have a mechanism with a parallel configuration or with closed loops, it is not so easy to obtain the linear and angular velocities or the acceleration of all the links, and this is primarily because of closed loops. Okay, and it's also because there are many more joints than the degrees of freedom. So we will take an example of a 3 RPS parallel system. The 3 RPS mechanism looks as follows. So we have a top moving platform, which is this. There is a fixed base platform, and between the top moving platform and the fixed base there is a rotary joint, a sliding joint and a spherical joint. So the 3 RPS means that there are 3 of these serial chains, and each serial chain contains a rotary joint, a prismatic joint and a sliding joint. Okay, and in order to analyze or model or solve this mechanism, we assign a fixed coordinate system which is called the base coordinate system. This is attached to the fixed base platform, and then we have these vectors which can locate from a fixed origin, which is O, and this is the x, y and z axis. The x axis is chosen such that it is going through one of the joints. Okay, so we will find out what are the degrees of freedom of this mechanism, and also the basic idea is that we want to locate these 3 spherical joints by these 3 vectors. So there is a base S1, base S2 and a base S3, which are nothing but the vectors from O to the spherical joints S1, S2 and S3. We also have a moving platform, so hence we have chosen a point which is the centroid of this moving platform. The moving platform has been chosen to be a triangle, and in particular an equilateral triangle for simplicity, and this point is the centroid, and we will locate this point using a vector base P with coordinates x, y, z. We would also need the orientation of this moving platform, and that we will see can be obtained by means of some vectors which we will define on this top platform. So for example, one such vector is from the spherical joint to the centroid. So this is P minus base S1, because this vector is P, this vector is base S1, so this vector along this direction is P minus base S1. So if you look at this 3 RPS parallel system, so the number of links is 8. So they have 1, 2, so one moving, one fixed base, and then there are 3 links in 2 links in each of these chains. So there is 1 link here and 1 link here. So that is 3 into 2, 6 plus 7 plus 1, 8. The number of joints is 9 because we have 3 rotary joints, 3 prismatic joint and 3 spherical joints. So J is 9. Lambda in this case is 6 because this whole mechanism operates in 3D space. We can also find the degrees of freedom of each one of these joints. So the 6, 1 degree of freedom, which is the rotary and the prismatic joints, so that is 6 into 1. Each spherical joint has 3 degrees of freedom, so that is 3 into 3, total is 15. So the degree of freedom can be obtained as lambda into n minus j minus 1 plus the summation of all the degrees of freedom at the joints. So if you substitute there, so you will get 3 degrees of freedom. So what this means is that there are only 3 joints which can be actuated. So we will consider this sliding joints or this prismatic joints as the actuated joints, and the variables, which is the sliding member, is L1, L2, L3. So these are the translations of the prismatic joints. So if you consider these as the actuated joints. So the 3 rotary joints are passive joints, and these 3 spherical joints are also passive joints. So we do not have any motors which are driving this rotary or the spherical joints. So in order to solve the kinematics of this mechanism, we have to find equations which will eliminate the passive joints, and basically we need to derive constraint equations. Okay, so for example, in the 4 bar, we had seen some constraint equations earlier. So how do we derive this constraint equation? So as I said, we will first find the position vector of this 3 spherical joints, S1, S2, S3. These are denoted by base S1, base S2, and base S3. So with a little bit of effort, you can see that the position vector is given by B minus L1 cos theta 1. Theta 1 is the rotation at the rotary joint 1. Okay, this is B, the side of this, the length of from O to this rotary joint is B. So basically it is a centroid, it's an equilateral triangle, and the radius of the circle subscribing this equilateral triangle is B. Okay, so this will be B, this is L1 going this way, this angle is theta 1, so hence it will be minus cos theta 1, L1 cos theta 1. The y coordinate will be 0, okay, and the z coordinate is L1 sin theta 1. So the z coordinate is going along this vertical direction. Likewise, with a little bit of more effort, we can see that the base to S2 is given by minus b by 2 plus L2 by 2 cos theta 2, and then we have a y coordinate in this case, which is root 3 by 2b minus root 3 by 2 L2 cos theta 2 and L2 sin theta 2. So b is the radius of this circumscribing circle of this base, okay, and a will be the radius of the circumscribing circle of the top platform. So we will see what this a and b numbers are later on in a numerical example. Finally, we can also find base S3, which is minus b by 2 plus half L3 cos theta 3 minus root 3 by 2b plus root 3 by 2 L3 cos theta 3 L3 sin theta 3. So this is basically simple vector algebra. We can find vectors and then we can see the components of each one of these vectors. So as I said, the base is an equilateral triangle circumscribed by a circle of radius b. So once we find out these vectors which locates this spherical joint S1, S2 and S3, we can find the length between base S1 and S2. So this is one of the sides of this top equilateral triangle, and this distance is constant. So this is also sometimes called as the SS pair constraint, which we had looked at earlier. So this magnitude of base S1 minus base S2 whole square is denoted as K12 square, and as you can see, the vector from 0 to base S1 will contain L1 and also theta 1. The vector from 0 to S2 will contain L2 and theta 2. So this constraint equation will be a function of L1, L2, theta 1, theta 2. Likewise, we can also say that the distance between S2 and S3 is constant, which is K23 square. So this is base S2 minus base S3 whole square is K23 square. And similarly, S3, the distance between S3 and S1 is also constant. So this is base S3 minus base S1 whole square is K31 square. And similar to the first equation, the second equation will only contain L2, L3, theta 2, theta 3. Okay, and the third equation will contain L1, L3, theta 3, theta 1. Why? Again, go back to this definition of what is base S1. This contains L1 which is this way, and theta 1. What is base to S3? This will contain theta 3 and L3. So this distance, which is the difference between this point and this point, will contain only L1, L3, theta 1, theta 3. Okay, so what do we have here? We have three equations, And in these three equations, you can see that L1, L2, L3 are actuated joint variables. So we would be given the values of the actuated joint variables. We have 3 degrees of freedom. So 3 of those joints will be known. So in this case, we have assumed that the prismatic joint variables are known. So we have 3 equations, and there are 3 passive joint variables, which are what? Theta 1, theta 2, and theta 3. So we should be able to solve for theta 1, theta 2, and theta 3 analytically or numerically. Okay. So what is the problem? So we are given L1, L2, L3. We have to first find theta 1, theta 2, and theta 3. Okay. So once we obtain theta 1, theta 2, theta 3 for a given L1, L2, L3, we can then specify or find these vectors base to S1, 0 to S2, and 0 to S3. Okay, so we know these 3 vectors. So the centroid of this top moving platform is 1/3 the sum of these vectors, and that is because we have assumed this triangle to be equilateral triangle. If it is not an equilateral triangle, then there will be some relationship between the 3 vectors or the 3 points. The orientation of the moving platform can also be found once we know theta 1, theta 2, theta 3 for a chosen L1, L2, L3. Again, we have these vectors, from S1 to P. So what is S1 to P? We know P because this, from the previous step, we know what is this vector. We also know base S1, so this is this direction. Okay. We can also find similarly P to S3. Okay, so we can find this vector, a direction from S3 to P. So we have 2 vectors in a plane. Okay, so the cross product of those 2 vectors will be along the Z direction, which is what is shown here. So the x-axis is along this vector as shown here. The cross product of this with this vector is the z-axis, and that is shown here, and the y-axis is the cross product of z cross x. And why do we divide by the magnitude? Because we need unit vectors. So this vector between base P minus base S1 is not a unit vector. So when you divide by the magnitude, you will get a unit vector. Similarly, we divide by the magnitude of the cross product and we get a unit vector along the z direction. And y is z cross x. So we have defined the x-axis of the moving platform, the z-axis of the moving platform, and the y-axis of the moving platform. And hence, we know the rotation matrix, because again, if you go back and remember, any rotation matrix is the moved or the xb in a coordinate system, yb in a coordinate system, and zb in a coordinate system. In this case, we have basically xb with respect to the base coordinate system, yb with respect to the base coordinate system, and zb with respect to the base coordinate system. So the position vectors of the centroid of the top moving platform and the rotation matrix giving the orientation of the top moving platform with respect to the base, they are very, very long and complicated. In fact, if I start writing them, they will not fit into this page. So the analytical expressions are too long, but they can be derived. They can be derived using computer algebra systems. So we have used Maple, which we will discuss later, of how to derive these expressions. Instead, in this slide, I am going to show you numerical results. So to obtain numerical results, we first choose some of these parameters. So the radius of the circle circumscribing the top platform A is chosen as 0.7 meters. The radius of the circle circumscribing the bottom platform B is chosen as 1 meter. And this is the 3 degree of freedom mechanism. So there are 3 actuated joints, and these were chosen to be the sliders, P1 prismatic joints. So we will assume that the sliding at the prismatic joints are denoted by L1, L2, L3, and they are like 1.2, 1.0, and 0.8 meters. Okay, so once we have those loop closure constraint equations. Remember, we had three constraint equation, eta 1, which was a function of L1, L2, theta 1 and theta 2. So again, using Maple, we can simplify that equation and we will get a reasonably complicated expression like this. So the first equation is 3 minus 3a square plus L1 square plus L2 square, and then L1 and L2 cos theta 1 cos theta 2 minus 2L1 L2 sin theta 1 sin theta 2 minus 3L1 C1 minus 3L2 C2. This is equal to 0. So as expected, the first equation contains only L1, L2, theta 1 and theta 2. So C1 here means cos theta 1, C2 here means cos theta 2, S1 is sin theta 1, S2 is sin theta 2, and so on. The second equation, which was between 2 and 3, the spherical joint 2 and 3, will contains L2, L3, theta 2 and theta 3, and it sort of looks very similar, and it is 3 minus 3a square plus L2 square plus L3 square plus L2 L3 C2 C3 minus 2L2 L3 S2 S3 minus 3L2 C2 minus 3L3 C3 equal to 0. And the third equation is the distance between S1 and S3, which is constant, and we are going to assume that it is circumscribed by a circle of radius a. So hence, since it is an equilateral triangle, the sides are of length a root 3. Okay, so the third equation is 3 minus 3a square plus L1 square plus L3 square plus L3 L1 C3 C1 minus 2 L3 L1 S3 S1 minus 3 L3 C3 minus 3 L1 C1 equal to 0. So these are three nonlinear transcendental equations. So we have sine theta, cos theta, and product of sine and cos, and so on. So this we cannot solve very easily, but again we can solve it numerically. And MATLAB gives us solver of algebraic equations like this, something called fsolve. So in fsolve, we substitute these three equations and give some initial guesses, and then we can find the values of theta 1, theta 2, and theta 3. So in these equations, we substitute L1 as 1.2, L2 as 1.0, L3 as 0.8, and then we give it to fsolve, and this will give you theta 1 as 1.235, theta 2 as 1.348, and theta 3 as 0.217 in radians. Okay, so this is numerical solution because the analytical expressions are much too complicated. For this particular parallel mechanism, analytical expressions are also available. So once we have found out theta 1, theta 2, theta 3 for the chosen L1, L2, L3, we can go back and substitute the values of L1, L2, L3 and corresponding values of theta 1, theta 2, theta 3 in the vectors base S1 plus base S2 and base S3, and then we take the 1/3 of all sum of these three and we get the position vector of the centroid, and that we can obtain in this expression. The numerical values are 0.0352, 0.1617, 0.7601 in meters. The rotation matrix can also be found out, as I had explained. The x-axis is between S1 and P. The z-axis is the normal to the top platform, and y-axis is z cross x. So we will get a 3×3 rotation matrix. The first column is the x-axis, the last column is the z-axis, and this is the y-axis. So we will get 0.814 minus 0.231, 0.533, and likewise for the z-axis is minus 0.533, minus 0.662, 0.527. So these are given up to third place of decimal, and this is the y-axis. Okay, we can also go on and find the velocity of the centroid. So for that we need to take the derivative of the position vector which is given by this. Of course, we have to take the derivative of the analytical form of the position vector, and when you take the derivative, you will get L1 dot, L2 dot, L3 dot, and theta 1 dot, theta 2 dot, theta 3 dot. They will contain all these terms, and also of course L1, L2, L3, and cos theta 1, sin theta 2, and all those trigonometric functions. So for obtaining the velocity of the centroid, we have chosen L1 dot as 0.12, L2 dot as 0.1, and L3 dot as 0.08 meters per second. The theta dot can be also obtained from again the loop closure equations, or the derivative of the loop closure equations, and they are given by theta 1 dot is 0.1235, theta 2 dot is 0.1348, and theta 3 dot is 0.0217 radians per second. So once I have these values for the L dots and theta dots, the linear velocity vector of the centroid, which will contain L dot, theta dot, and also L and theta, can be obtained, and we can substitute, and we will get 0.0263, 0.2323, and 0.9939 meters per second. The angular velocity vector can also be obtained from obtaining R dot R transpose. We have seen how we can obtain the angular velocity from the derivative of the rotation matrix and obtaining the skew symmetric matrix, and then extracting the three components in the skew symmetric matrix, which is exactly what has been done. And you will get 0.753 as the x component, so this is omega x, minus 0.968 is omega y, and 0.148 radians per second. This is the z component. So as you can see, in the case of parallel system, the work is much more than in a linear chain. In a linear chain, we can go from base to the end effector or to the last link and obtain linear and angular velocities and even accelerations. Here we have to use the loop closure constraint equations. We have to find the values of the passive joint variables in terms of the active joint variables. So a lot of numerical work has to be done, and that's why analysis of parallel chains is much more complex than a serial chain. So in summary, the serial chain with R and P joints, one fixed and one free end. The position of a point of interest in a serial multibody system can be obtained from multiplying 4x4 homogeneous transformation matrices. Parallel chains, there is no clear free end and presence of loops. The position of a point of interest in a parallel multibody system often is a point chosen on the moving platform. The rotation matrix in parallel chain requires choice of output and free end. The linear velocity is the time derivative of the position vector. Angular velocity is obtained from R dot R transpose, and accelerations are obtained from time derivative of the velocity vector. And I described to you how we can obtain propagation formulas for serial chains containing R and P joints. For parallel systems, there is no propagation formula.